Okay, so in chapter 3.1, we're going to work on solving linear systems by graphing. Now, first of all, a system of two linear equations and two variables, such as x and y, also called a linear system. And that is because it consists of two equations that look like the following, where we have ax plus by equals c and dx plus ey equals to f. Now, the a, b, the c, and d, e, f, they all represent constants. Where you see it with the x and y, they represent coefficients. And coefficients are the numbers that are in front of the variables. They are capitalized to just make sure that you know the difference. Now, the way that it works is that both of these must be satisfied in order for them to be a correct linear system. And so a solution of that system of a linear equations in two variables is when you have an ordered pair that satisfies both of them. Now, there can be cases where they will not work, as you will see soon. We're going to check to see whether the ordered pair 5, 6 is a solution of the system. All right, we're going to start with number 4. So we're going to substitute in. The solution to see if it does work. All right, so we have negative 2 times 5, that's our x value, plus 4 times 6, and we want to see if that equals to negative 14. So negative 2 times 5 is 10, negative 10, plus 4 times 6 is 24. Does that equal to negative 14? Negative 10 plus 24 is positive 14, and so we can see already that this will not be a solution, as positive 14 is not equal to negative 14. We can also just check to see how it will work with the other one. We already see that it's not. As long as one fails, the whole thing fails. But just to show you, we have 3 times 5 plus 6. Does that equal to 21? You have 15 plus 6 equals to 21. And 21 does equal to 21. So it passes for the second one, but the first one doesn't. And because just one is needed to fail the whole entire, then this one does not work. It's not a solution. All right, let's try number 5. Number 5, we have 7 times 5 subtract 2 times 6. Does that equal to 23? 7 times 5 is 35. Subtract 2 times 6 is 12. And we should be able to see that that will be equal to 23. So far, the first one works. We want to check the second one now. Negative x would mean negative 5 plus 3 times 6. Does that equal to 13? So negative 5 plus 3 times 6 is 18. And negative 5 plus 18 will give us 13. So because both of these work, then yes, this is a solution. And then the last one, number 6, we want to see if this one will be a solution or not. And so we substitute that in again. So we have 5 plus 6. Does that equal to 11? Yes, it does. So we know the first one is a solution. That is a solution to the first equation. Now we try the second one. And you should be able to see that if you know the properties of algebra. Negative, if you substitute that 5 in, subtract this 6. Does that equal to negative 11? Negative 5 subtract 6 does equal to negative 11. So because this one works for both, then yes, 5, 6 is a solution to the two linear systems, number 5 and number 6, but not number 4. All right, so now let's go to solving them to see what does it look like when we actually graph a linear system. And we're going to use that to solve our equations. Just as we learned under functions that we can represent different functions or equations via a numerical representation, tabular, meaning using tables, graphical, even through mappings. So let's go ahead and solve this system. We're going to see what happens graphically and make some sense out of this. All right, so let's go ahead and work this one out. In order to solve this one correctly, what you're going to notice is we're going to have to do a method of just graphing. All right, so let's go ahead and graph these using the first method of okay, so let's graph this. We could use either the slope-intercept form, or we can use our x and y intercepts using the standard form. For the first one here, I'll make this one purple. That one's easy. We could see if we set x equal to 0, y would be equal to 3. And if we set y equals to 0, x will be equal to 3 using the x and y intercepts. So we know that the graph will look like this. It'll come straight through. Remember, use a ruler. All right, so that's our first one. That represents the x plus y equals to 3. Since there are more than one line, we definitely want to label that graph. Then we need to graph the other one, the first one. And we could do that one the same way. We could use either slope-intercept form, or we can use our x and y intercepts. For this one, if we use x and y intercepts, you remember you set it equal to 0, so you're going to end up with some decimals. You could also change, or fractions. You could change it to the slope-intercept form if that's your preference, but you see that you still are you going to end up with fractional type answers. So let's go with the x and y intercepts on one side and the slope intercept on the other. All right, so if we do slope intercept form, we have 2x subtract 3y equals to 1. We want the y by itself and we want it positive, so I'm going to bring that over. I'm going to do it all in one step, so bring the 1 over as negative 1 and take the negative 3y over as positive 3y. In order to get the y by itself, we have to divide by 3 everywhere. Alright, so I'm just going to rearrange it so y is on the left side is equal to 2/3 x subtract a third. So you could choose to do it slope-intercept form that way. Find negative a third here on your graph. You could estimate it. I have a decimal chart this time, so or line axis, so it makes it easier for me. Or if we do the x and y intercepts, you would first do x-intercept, or y, doesn't really matter, first. So to find the x-intercept, set your y equal to 0. And so you have 2x is equal to 1, so x is equal to 1/2. And if you do the y-intercept, then you set your x equal to 0, and then you see that that cancels. And in order to find that, you're going to have y is equal to negative a third. And the same thing you see over here, negative third. All right, so you could use either one of those now to graph by finding a half on the x-axis and negative third on the y-axis, and then just connecting your lines. And we're going to do that right now. A negative third, well, you can see where negative 0.5 would be. Negative 0.4 would be right above it. Negative 0.3. So remember, a third is 0.333. So it'd be pretty close, and mine is not going to be right on the money, but it's going to be as close as possible. So it's about there. That's a negative third. And on the x-axis, a half is about here. And so basically that line is going to go straight through that. All right, so we're going to try to draw this as smooth as possible. And this one is the graph 2x minus 3y equals to 1. Now let's think about what we're looking for in order to solve this. When we just solved in the previous one, we were looking for a coordinate point that would satisfy or be the solution to both equations. Now remember, in previous chapters, we learned that in order for a point to be a solution to one equation, then it has to be a point on the line. So in order for this to be a solution to both equations, this means the point must be on both lines. Now looking at this graph, is there any place where one point can be shared by both lines? Well, if you guessed the intersection, you are correct. The intersection represents the point that lies on both lines. And that's our point 2, 1. And if you was to substitute the point 2, 1 into each of those equations, like we did in the previous one, you will see that 2, 1 satisfies both of them. 2 times 2 is 4, right? Substituting 2 into there. 3 times 1 is 1, and 4 subtract 3 is 1. And 2 plus 1 is 3. This is the solution graphically that satisfies the linear system algebraically. And that's how you solve a system graphically. You see where the two lines intersect. Alright, so let's see if we can figure out how many solutions that a linear system has based off of the graphs. And this one here, what you're going to see is we already did one with an intersection. Let's see what happens with different scenarios. So here it's the solutions to this. We can graph each one by finding the x and y intercepts. And hopefully after a while you could just start doing the x and y intercepts in your head. So the x-intercept here is going to be 2, right? Because if this is 0, it disappears, and 6 divided by 3 is 2. All right, and then to find the y-intercept of that one, you could do the same thing. The 3x is basically disappearing because it's set equal to 0, and you're going to divide 6 by negative 2, which would be negative 3. All right, then you could do the same thing for the bottom one. All right, so we could do the same thing here to find the x-intercept. If we set y equal to 0, it basically disappears. You could put your finger over that as well. And 12 divided by 6 is going to give us 2. And then we could do the same thing on the this side here. We could set x equal to 0, and that leaves our y, and 12 divided by the negative 4, y is going to give us negative 3. And look at that, we have the same x and y intercepts. Now, if we have the exact same x and y intercept, what does that say about our line? Well, what it says about our line is that we have the same line. X is equal to 2, and y is equal to negative 3. And if you were to graph that line, that's both lines. So what we have here is that when we have equations that gives us the same line, we can have what's called an infinite amount of solutions, because both of these lines go on forever in either direction. That means there's a point here, there's a point there, there's a point there, and then if you zoom in, there's an infinite amount of points in between those 2 points. So there's an infinite amount of solutions. So whenever you get a line that is exactly the same, when you graph it, you will see that they are infinitely many solutions, since that line goes on for an infinite direction, and because you can get an indefinite amount of points in between each point if you kept zooming in. Now what we want to do is look carefully at the relationship between these. Notice that if I multiply the first equation by 2, then I get the exact same equation below. 3x times 2 is 6x. Negative 2y times 2 is negative 4y. 6 times 2 is positive 12. And so basically, these are multiples of each other. And whenever you get equations that are multiples of each other, that's one of the quickest ways to see whether or not you will have an infinite amount of solutions. That's how you will know, just by seeing if they are multiples of each other, whether that's a multiple of 2, or if you see that 1 has been divided by 3, etc. Any relationship where they have the same multiples for the x, y, and the constant, then it's correct. Now, if you were to solve each of these into the y-intercept form, what you'll see is that you get the exact same y-intercept once you reduce your fractions. So I'll show you quickly over here. For the first one, if we solve this one for y, just bear with me, I'm going to skip some steps there, but you have 2y, negative 2y is equal to negative 3x plus the positive 6 that's there. If you divide everything by negative 2, then you're going to get positive 3 halves, right? X plus 3. Having some issues with the pen. So we have y equals to 3 halves x plus 3. If we were to do the same thing for the second equation, and I'm just going to skip some steps here again, and just going to bring that, it's probably easier if I brought the 4y over to make it positive. But we're going to have 6x subtract 12, and on the other side, it's going to be positive 4y. All right, so once we divide everything by 4, and I kind of worked that one backwards, hopefully it didn't. All right, so we get y is equal to 6 over 4, it reduces down to 3 over 2, x, and negative 12 divided by 4 is negative 3. So we get the exact same thing. Notice here I had changed that. I had made a mistake and not divided it by negative, so just fix that. But you get the exact same thing if you did it through slope-intercept form. And so basically, whenever you have it in standard form and they are multiples of each other, you know it will be infinitely many solutions. If it's in slope-intercept form, you see that they are exactly the same equation once simplified. All right, let's try the second one, part B. So far we saw we had a unique solution, and we get that one solution that works. Here we see infinitely many, and let's see what we get here for part B. Alright, so we have 3x subtract 2y equals to 6. Notice they're very close, but there's a difference here. So this is not the same as a. So be careful of those ones. Let's see what happens when we work this one out. So first we start off with our x and y intercepts. Remember, you can cover one of them to find your x-intercept. Set your y equal to 0. And 6 divided by the 3 is going to give us x equals to 2. When we find our y-intercept, remember it's the other way around. You're going to set your x value equal to 0. And you have negative 2y equals to 6. And 6 divided by negative 2 is negative 3. All right, let's move on to the second one. We'll do the same thing here, but now we have a 2 on the other side. So to find our x intercept, set your y equal to 0, basically disappears. And x is going to be equal to 2 divided by 3. And then to find the y, you set your y equal to 0. Sorry, your x equal to 0. And when you set your x equal to 0, you're going to have 2 divided by negative 2, and that's going to give negative 1. All right, so now that we have that, we can go ahead and graph. If we do that, x is equal to 2 for the first one, and y equals to negative 3. Right, you draw your line through, and make sure you label it so you know which one is which. So that's your 3x subtract 2y equals to 6. And the other one, I'll change the color. We have x equals to positive 2/3, and 1 is here. Halfway is in between the 0 and the 1, so 2/3 will be somewhere around there, right? And then we have y equals to negative 1. And when we connect that line, there we have it. What you see is that these are parallel to each other. And if you know anything about parallel lines, as we talked about before, when we learn how to graph parallel lines and perpendicular lines, parallel lines do not touch. They will never touch because they go on in the same direction forever. They will never intersect. And if they never intersect, they can never have a unique solution in between the two of them. So this one would have no solutions. And because you already know about parallel lines, you should remember they have equal slopes. So if you were to work this one out into slope-intercept form, you will see that they have the same slope, but they will have different intercepts. So when you have parallel lines or equal slopes, then you know you have no solutions. But if you have equal slopes and equal y-intercepts, then what will happen is you will have infinitely many solutions. So we can summarize that as seen in the book into the 3 different scenarios that can happen. You can have exactly one solution, you can have infinitely many solutions, or you could have no solution. Remember, these are parallel lines. These are lines that are exactly the same, right? So equal lines. And remember, if it's in standard form, the way you can tell whether they're equal in a graphical representation, is if they're multiples of each other. And then the last one is the unique solution, and that happens when you do not have the other 2 scenarios. As long as you have an intersection, you will have a unique solution. All right, so here are some other examples here that you could read from the book in your personal study.